Okay, thanks very much for the kind introduction. I'm very excited to be invited to be giving this talk today. And first off, before I start my talk, I quickly want to thank the organizers for putting together such an amazing program. I'm very much looking forward to seeing all the presentations today. For us humans, manipulating objects are super easy. We learn to do so from a young age without much effort. Even if we encounter new...
Sorry. I think it's okay. Now it's good.
Okay. So, even if we encounter new objects, it's fairly easy for us to adapt to unseen geometries, manipulate objects we have never seen before. Well, this is very simple for humans. Modeling these tasks is extremely difficult, especially when it comes to robotics, because it involves a lot of complex, high degrees of dexterity, and also some interplay between different sensing capabilities, such as tactile and visual sensing. Some efforts have been made, mostly in the vision and graphics community, to capture a lot of data of humans interacting with objects, such as the graph dataset, Arctic, or DXYCB. The reason why this is potentially useful for robotics is that we can use this data as demonstrations, then map it to a humanoid, maybe first in simulation, but then finally our end goal would be to put this onto a real robotic system. However, one of the issues with these data sets is that motion capture is inherently expensive. So it requires a lot of engineering efforts, it requires participants, and each time we want to gather more data, we need to go back into the motion capture studio and find more participants and collect new data for new objects. So the question we asked in our research is, can we learn a model that generates physically plausible and human-like motions of hand-object interactions without relying on motion capture or video data? How can this be potentially useful? So the first one I already mentioned. So if we look into robotic grasping, such a model could serve as like expert demonstrations that scale beyond what we have for motion capture. Secondly, more in the vision community, this could be useful for data augmentation, where we can augment the data for like estimation models. And lastly, as we have shown in some of our research, we could use such synthetic data for human-robot interaction, where we take the simulated humans and we train robots with it. So I want to delve into these questions by talking about 3 of our papers. And the first one answers the question, how can we generate dexterous grasping with a single hand and rigid objects? We then extend this to articulated objects and two-hand manipulation. And lastly, I want to talk about how we can scale this up to more than 500,000 objects. So let's start with the DGRASP paper. So back when we submitted DGRASP, there were a lot of works that looked at these hand-object interaction data sets and then used models to predict single frames of grasping. So like given an object mesh, what is a human-like grasp? But the problem with these models is that they didn't look at the temporal aspect. So these were not sequences, these were single frames. Also, because these models are purely data-driven, there's a lot of physical artifacts such as interpenetration. Hence, we introduced DGRASP as a framework to generate physically plausible hand-object interactions by leveraging physical simulation and reinforced learning. While this was a first step, we still needed to assume that we have access to some sort of human supervision. So instead of relying on full video demonstrations, we assume that we have access to a single hand pose in space, which is the point where I grasp an object. So for example, if I have this bottle, how do I roughly want to grasp it? Do I want to grasp it from top or from the bottom? So we split this task into 2 distinct phases. The first one is the approaching and the grasping phase, and the second one is the motion synthesis phase, where we move the object into a target 60 pose. This is also reflected in our model. So we split it into a grasping part, which learns the approaching and the grasping, and the motion synthesis part, where we move the objects into a target pose. So as I mentioned, we assume that we have access to a single grasp reference that tells us roughly how we want to grasp the object. And this is a local hand pose relative to the object. We then do some feature engineering to make this into object relative space and feed this into a grasping policy, which predicts action in order to move the hand towards this target grasp. So if we look at the state space that we're using or the features that we're using here, because we are in simulation, we can make use of all the privileged information that we have. So we use a combination of proprioceptive sensing and object information. And then we also have some goal features that incentivize the policy or let the policy know about where it is exactly with respect to this target grasp reference. So here's our full loop. So we have a policy that predicts actions that move the hand in the physical simulation. We do standard PD control to compute torques, which we apply to hand and get an updated state space. In our reward function, we do a combination between positional rewards and contact rewards. And this is quite crucial because a lot of these references that we get, they have some interpenetration. They may not be exactly in contact with the hand. So by doing a combination between rewards that incentivize imitating a certain position and actually achieving contacts with the objects, we can kind of get rid of some of the noise in the data. And then for the motion synthesis part, I won't go into too much details. The main insight here is that we keep the grasping policy active. And this means that the fingers still exert enough force on the object to grasp the object, whereas we take over the control of the global pose of the hand. Because everything is modeled in object relative frame, even if the object moves into a totally unseen global position, the policy can still manage it because it is only in relative frame and it's still in a similar position to what it has seen during training. Okay, and then just a few training details. So we use PPO, race and physical simulation, and we create a controllable hand model based on the popular Mano model. We train a single policy over all the objects we have in the training dataset, and then test on unseen pose references. Okay, let's come to some results. So first, one advantage that we have is that because we are in a physical simulation, we can sort of denoise some of these artifacts that we see in this static grasp synthesis methods. So as you see on the left, there's some interpenetration. And after we feed this into our method, we can get rid of these object interpenetrations because in the physical simulation, this is not possible. Okay, and then we want to show that this is also practical, that we can take a single image of a human hand grasp, use some off-the-shelf pose estimator, and then from this single grasp, we want to make dynamic sequences out of it. So you see, we can then feed this single grasp into our method and generate sequences that are dynamic. And here's just a couple of more examples of our method. So you can see we can also do functional grasps, such as grasping handles. And also there's a lot of diversity in like the object poses that we can move into. And here's just a couple of more examples of what it looks like when we use our policy. Okay, so this was single-handed rigid object grasping, but in the real world, we actually manipulate objects usually with both hands. And also a lot of objects that we use are, let's for example, say the laptop, are articulated. So in RDGrasp, we extend our dgrasp work to bimanual manipulation and also to articulated objects. So the goal here is not only to grasp objects, but grasp objects potentially with two hands, and then also articulate them into target poses. So while the task is new, the philosophy that we use here is similar. So we again use physical simulation and reinforcement learning. And we assume that we have access to single frames of grasps that tell us roughly how we want to start the manipulations. So I won't go into the technical details because also we will have a poster in this workshop where you can come and talk to us if you're interested in more of the technical details. I just want to give the main insights. So what we had to do to get this to work is extend the state space to also include information about articulation of objects. And we also had to reflect this in the reward function because now we also want to achieve articulation. Similarly, we had to add some techniques like curriculum to make training like starting from easy to more difficult to get this to work. So if we compare this to our previous work, you can see that grasping is possible with D-grasp, even with two hands, but the articulation of the object is quite hard to achieve. Whereas with our new model, we can actually relocate the objects and then also articulate them into target articulation angles. Again, we wanted to show that this is potentially practical by using a single image of a hand manipulating the objects. As you see, again, there's interpenetration. And we can then feed this into our model and generate a dynamic sequence that manipulates and articulates the objects. And here's just one more demonstration that shows how we can actually generate longer sequences of manipulating multiple objects, articulating them, for example, putting this object into the box and then closing the box. Okay, so we have covered single-handed grasping. We looked into articulated objects and two-handed grasping, but in practice, it may be quite difficult to find coupled human hand references with objects in the wild. Also, this means we have to assume that we know the object mesh, which of course in the real world is not always feasible. Also, we have focused only on the human hand so far, but we are also interested in robotic hands. And lastly, we want to do grasping at the larger scale. So this brings me to our upcoming ECCV 24 paper called Grasp XL. The question we ask here is whether we can generate hand-object interactions on a large scale for many different hand morphologies without relying on these grasp references that we have been using before. So recent efforts have shown that we can get more and more object meshes such as Obtraverse and Obtraverse XL. So we're interested in grasping on a scale that these data sets have brought. Also, we want to be able to follow multiple objectives. This can be, for example, how I want to approach a certain object. And we want to be able to have this more general across different hand morphologies. So just to give you some insight into what we mean by objectives, this could, for example, be like an affordance area on the object. It can be an affordance area plus some approaching direction. It could be just the approaching direction from which I want to grasp the object, or it could be the approaching direction plus some point on the object that I want to make sure is grasped by the hand. So what are the challenges here? So first of all, the policy has to be able to generalize across a very wide variety of object geometry. Secondly, it has to be able to do this for multiple objectives, even combinations of them. And then it has to work across different hand models. Again, we're using reinforcement learning and physical simulation to achieve this. Our framework is trained on only 58 objects, but can then generalize to many combinations of different objectives. It works across over 500,000 objects, and it works across different external hand morphologies. So to deal with the multiple objectives, we introduce a technique called objective-driven guidance, which on a high level helps the policy be biased towards following these objectives. To make the policy work for different hand models, we found a reward function that is robust and doesn't need to be changed or like hyperparameter tuned, that kind of combines grasping reward with an objective reward. To deal with the diverse object types, we introduced some local sensing of the geometry by looking at the distances between the joints and the local object mesh. And then we also introduced some learning curriculum that helps us deal to achieve stable grasping and following the objectives. So what we do is first, we focus more on following the objectives and we fix the objects in space. And in the second part, we focus more on the grasping and make the objects non-stationary. Okay, so we ran results on ShapeNet, PartNet, and Objaverse, and can achieve success rates of over 90% in terms of grasp stability without requiring any 3D hand object data. We also show some use cases. So we took 3D Fusion to generate an object mesh. We can then define some objective like grasping from the top. And then we just feed it into our policy at inference time, and it can generate you a grasp. Similarly, we took a method that can take an input video, reconstruct an object mesh from that video. Then we feed it into a policy together with an objective. And you can see our policy generates a grasp that is feasible and doesn't drop the object. Then we show like generalization across different hands. So as you can see, we can define some objectives and then just use this across different hand morphologies. Lastly, we can do per object, we can define different objectives. And you see that there's like a lot of diversity in the grasps that we can generate even for one single object. So in summary, our main motivation was that motion capture is inherently expensive. So we show that motion generation for dexterous HOI is possible, first using static priors, which we call hand pose references, in dgrasp and RDgrasp, and then driven by objectives on a very large scale without relying on any pose references. So GraspXL took a step towards generalization, but of course there's still room for improvement. So again, in GraspXL, we didn't look into articulated objects yet, and also it's a single-handed model. So making this work for multi-hands and articulated objects is still an open question. Also briefly want to shout out, of course, there's many concurrent efforts by other groups, which I haven't mentioned, that look into similar directions. Okay, in terms of future work, I think one important aspect is actually we're doing this here in rigid body simulations, but of course humans have soft contacts, and looking into how we can go from rigid body to soft contacts is quite exciting. Then thinking about objectives, so right now we define very abstract objectives, but looking into text-based dexterous grasping could be quite interesting. And related to that, how can we actually find objectives that align with users' intent, especially when we think about robots being deployed in the real world in our daily lives? And then one important aspect which we don't look at currently in our work is the sim-to-real transfer. But we believe that GraspXL could enable a very cheap way to generate grasping data for many different dexterous hands, which can provide data for object shapes at a scale which is just not feasible to collect in the real world. Or it could even serve as a low-level controller, which could potentially be used in a teacher-student framework, where we use this policy as the teacher and then distill it into a policy that only has access to more realistic sensing that we have in the real world, such as, for example, vision-based sensing. Lastly, I quickly want to shout out some other ongoing research we have done in our lab in this direction. So if you're interested in doing this for full bodies, I recommend you to check out our 3DV paper on full body and object synthesis. We also have a paper under submission that looks into doing this for humanoids for over 1,000 objects. And then if you're interested more in the human-robot interaction side of things, I encourage you to look at the human-to-robot handover papers that are shown here. Okay, so this concludes my presentation. I also quickly want to thank all of my collaborators, without whom much of this work wouldn't have been possible. So thanks for your attention, and I'm happy to answer questions.
Well, I guess you guys still have some time to take one question.
Jetzt mal als noch, wenn es zwischen Namen und Vorschlüsse, I would really like to know what you see in real life when getting away from simulation with all these different kind of hardware, which is mostly for me important to get the simple effective. And how do you think is the impact on that when you go to the real from the simulation on the haptic feedback of different kind of sensory there and different kind of mechanical hands?
So just to understand your question correctly, you want to know how we can transfer this from sim to real, like in terms of haptic capabilities. Yeah, so I mean, we make a lot of assumptions right now in simulation. We just assume that we have access to exactly which points are in contact and how much force is exerted. And I think current force sensors are just not there yet to like be as accurate as we have like physical simulation. I think there's some interesting works that look into how we can distill this from like sim to real by like there's some work from Deepak Pathak that looks into quickly like fine-tuning to new sensing capabilities in the real world. So you have some model that can quickly learn to adapt even if the sensing is a bit different from what we have in sim. And I think this could be like an interesting direction to take to do this.
Okay, Sammy, thank you.
Yeah.